Welcome to the course on two-dimensional signal processing, principles and practices. Continuing with the aliasing on what we had done due to sampling in the previous lecture, and how are the sinusoids gets aliased during the sampling. We'd see them, and what is the apparent frequency really you get it if sampling frequency is violated, and how do we look at that as a multiple folding during the aliasing. And then we look into the Fourier analysis for one-dimensional as well as we'll continue with the two-dimensional ones. So the aliasing of sinusoids, if we take for example this sinusoids x of t are given, there are two sinusoids and one with sampled impulses. So here the one pink one is shown as a 11 Hertz sinusoid, and the other one is 1 Hertz, that's a small one here, which is 1 Hertz sinusoid. The impulses are shown for both. It is both of them are sampled at a rate in which the samples are common to both of the signals. That means when it can happen, like these impulses are samples of the 1 Hertz also, and these are samples of the 11 Hertz also. So this samples will be common for both the sinusoids if you sample it at a particular rate in which the difference of these two 11 Hertz and 1 Hertz is Fs, or it can be multiple integer of that Fs. So if it is sampled with 10 Hertz, then we would get the samples like this. Those are part of 1 Hertz as well as 11 Hertz. Is that sampling theorem is satisfied? That is, if it is 10 Hertz, then the 11 minus 1, 10 Hertz. 1 Hertz, yes, the maximum frequency is 1 Hertz, it should be 2 Hertz for the Fs. We are sufficiently sampling it at 10 Hertz, fine. But 11 Hertz, if we take, at least it should be having 22 Hertz sampling frequency. But if we sample it at 10 Hertz, then it is undersampling, or we are not following the Nyquist sampling theorem. In that case, this 11 Hertz samples appear as 1 Hertz sample. That's what we say, that as a high frequency component appear as low frequency component. That's the meaning of aliasing. So this is the aliasing of sinusoids. We'll learn more about this. So the root cause of aliasing is the sampling rate, that is 10 Hertz. It's adequate for low frequency, that is 1 Hertz, but it is not adequate for the high frequency. So now it would yield similar samples. What is the condition at which it can happen? So this sampling of sinusoid at Fs giving identical samples for frequencies separated by integer multiple of Fs. That Fs is the difference, we said it is 10 Hertz. That integer multiple of that Fs also results in such kind of samples. So it is consisting x of t as cos of 2 pi f t plus theta. Let's take this is f. So this f is having the fundamental or frequency f naught, suppose, and if we replace this f naught is mfs, f naught plus mfs. So in that case, what are the samples are here? If this simple f of t is replaced with f naught plus mfs t. So if we take it, the sample that is in the discrete domain, t equal to n ts, replace it here, and what we get is cos 2 pi f naught plus m fs, this is n into t. So if you multiply these things, and here it would result in 1, right. So the cos 2 pi f naught n t plus 2 pi mn, and fs into t is going to be 1 plus theta. So 2 pi mn results in 1, for this is m and n are integers here. So the term it is going to be, this is 1, fs into t is 1, and the term this doesn't change these samples. So it is equivalent to cos 2 pi f naught n t plus theta. So x of n, the original signal, is now we are getting it irrespective of this m and mfs. So that's what we are saying, that if the sampling frequency is integer multiple of it, then you would you will end up in the same samples to a 2 pi f naught n t theta. So the sinusoids whose frequencies differ by mfs produce the same set of samples. So what is the reconstruction in this case? So if the samples are reconstructed using the low pass filter, which is having the bandwidth fs by 2, the reconstructed signal has the frequency fa. That means this f what we had originally is now called FA. What is the earliest frequency we get if it is reconstructed? Suppose that is due to aliasing. FA, the apparent frequency is the modulus of Fs here, F0 plus Fs by 2 minus Fs by 2. Fs is the sampling frequency used, or the Fs by 2 is the folding frequency which we had seen in the spectrum. So, if we just take the multiple folding of the spectrum, we plot the frequency f, that is we used here F0, and the apparent frequency, and for us this folding frequency is important, that is Fs by 2, and this is minus Fs by 2. The frequency between minus Fs by 2 to plus Fs by 2 is mapped this way, that is from here to here, that is Fa, the apparent frequency, 0 to this point is fine. I mean the Fs by 2 is, there is no aliasing. So, from here Fs by 2 to minus Fs by 2, and then this portion till this Fs. So, we get the case where is that Fs by 2 to Fs. So, this is having the negative frequency. So, this needs a phase reversal that we had already looked into the last lecture. So, where is that phase reversal? What is the cause of it? This phase reversal is happen here. So, if we make the magnitude here Fa magnitude, so you can clearly see this is the portion in which this Fs by 2 to Fs is again positive, and this frequencies for which the phase, if the sinusoid is of this frequency, then there is need of phase reversal. We will see it through the example. Also Fs2 here 3 Fs by 2, so it's there is no case of phase reversal, but 3 Fs by 2 to 2 Fs, again the phase reversal would occur. So, these are the shaded areas which shows the phase reversal details. That means the frequencies lying in these regions needs the phase reversal. So, apparent frequency can be visualized like this: the sinusoid which is sampled at some Fs yielding the sample, and what should be the, there is aliasing or not, whether we had followed the sampling theorem or the sinusoids, how it is, how the apparent frequency is going to be, what the resultant frequency would be. So, that we would see through example. Continuous time signal, if we have the cos 2 pi ft theta and it is sampled at a rate of 1000 hertz. What is the earliest frequency or earliest sinusoidal frequency or the apparent frequency? If the signal frequencies are, this f is 400 and 600 different cases, we would 1000 and then 2400 and so on. We would compute Fa for each case. So, if we take this apparent frequency Fa, which is related with f minus m Fs, we said that this is going to be the multiple, Fs is integer multiple of it. Fa is between minus Fs by 2 to plus Fs by 2, and this is also equivalent to saying what we said, if we reconstruct it, that Fa would be F0 plus Fs by 2 modulo of Fs minus Fs by 2. So, they both are giving the same information here, it is not the different one, expressing in different ways. So, the Fs is 1000 and folding frequency now is 500 hertz. Now, for the case of first one, F is 400 hertz, then the folding frequency is 500 hertz. First check this frequency is less than 500 or Fs by 2. If it is so, then it is 400 hertz and then sampling frequency expressed is 1000. So, 2 times 400, and if even the Shannon sampling theorem, it should be 800. So, we are following 1000. So, there is no issue of aliasing in this case. So, it should be 800 hertz sampled, but the Fs is more than that, there is no issue, no aliasing due to sampling in this case. So, the apparent frequency or the reconstructed frequency would be 400 hertz itself, like we can recover it easily without with the low pass filter. And the second case, if we take the second case of f equal to 600 hertz, suppose the cos 2 pi ft plus theta, that is having frequency of 600 hertz and it should be sampled at least 1200 hertz to avoid the sampling, as per the sampling theorem, but this is sampled at 1000. So, what should be the frequency it would appear in the reconstructed ones? So, if the here, we can say from this Fa is f minus m Fs, that is f is 600 hertz, m into Fs is 1000. So, if we take this is minus 400 hertz, that means this 600 hertz, because of violating this sampling theorem, so it would appear as minus 400 hertz, minus This m, it should be a integer, smallest integer possible. You can take here is 1. Okay. So this minus 400, that minus sign refers to the signal needs to be phase reversed, because it is above 500, that is also, and that is Fs by 2, and it is below Fs even. So that portion needs the phase reversal. So this should be written as cos 2 pi 400t minus theta instead of that plus theta, the signal. So this is a signal we get during the reconstruction, not the cos 2 pi 600t plus theta. So this theta, note this 9 minus sign is this. So similar, this is aliased one. So actually we had the cos 2 pi 600t plus theta was the signal. Due to sampling after the reconstruction, it appears like this. So there is a aliasing. So if we take the third case, 1000 hertz and Fs is 1000 hertz, obviously it should be 2000 hertz, it should be sampled, isn't it? So but because of 1000 hertz in this apparent frequency, you can substitute here f, and m is the smallest integer, f 2000, and it gets this. So you can see the 1000 hertz signal appearing as DC, that is aliasing again. So the high frequency becoming low frequency here. So similarly in the previous case also. Now the fourth case here, we can take, this is 2400 hertz, because Fs is 1000 hertz here, and obviously this is also will result in aliasing. Is there any phase reversal or not? So here it should be at least sampled at 4800, but it is not so. So 2400 minus the closer value of this MFS, okay, so 2 into 1000, it is going to be resulting in 400. So the signal which we have here is, it's appearing as 400, though it doesn't require any phase reversal. Okay, so because there is no negative sign in it, it is going to be cos 2 pi 400 t plus theta here. So it would be, there is no phase reversal. In this case, it doesn't lie in this shaded region, so that's how it is getting the positive value of this. So shaded regions needs to be taken care when we use the sinusoidal sequences and sampling it, whether it is giving aliasing or not. The apparent frequency can be calculated in this fashion, and we can also pay attention to the phase reversal which is needed. And if we extend this sampling to 2D, two-dimensional one, so the same sampling theorem applicable to 2D as well. So let's take, this is a 2D sequence which has an x of sequences is x of n1 comma n2, where these samples are obtained from a continuous time sequence xc t1 comma t2, and t1 is replaced with n1 t1 and t2 is replaced with n2 t2. Okay, so this case, if you just replace this with n2, that's nothing but the sampling n1 t1 and n2 t2. So we get this sequence, that is 2D sequence. If we take the Fourier transform of it, then we get xc of omega 1 comma omega 2. Omega 1 and omega 2 are the frequencies here in the frequency domain. This omega c dash and omega c double dash are the band where it is limiting, or the cutoff frequency, we can say, the band limited sequence. If you recall that 1D sampling, we said B and minus B we used. So here that B is nothing but omega c dash in one direction, and the other one for n2 or omega 2 here is omega c double dash. So it is band limited in this way. Okay. So these are the cutoff frequency for the 2D signal. This is a Fourier transform of it. We got a pattern in the 1D sample, baseband pattern. So similarly here, this is the baseband in the 2D case. So the sampled one, if the sampled sequence, if we take the Fourier transform, it x of omega 1 comma omega 2, it's equal to 1 by t1 t2, and r1 varying from minus infinity to plus infinity, these summations, xc omega 1 2 pi t1, and this is omega 2 2 pi t2. So we used k also in the previous discussions. It can be k1 and k2 as well. For the 2 pi by t1 is omega s we used in the 1D case, omega s to omega s and so on. So this is due to the sampling we get. So omega 1 and the shifting operation of this k into omega, whatever the omega s or omega 1, what we can say, this is going to be the frequency 2 pi by t is omega. This is the sum, you can see, notice the summation of the spectrum, which is going to be repeated. Like in 1D, we had the repeated spectrum repeated pattern of the baseband due to the sampling. So this is the equation of that, and then this equation is obtained with the sampling frequency 1 by T1 is greater than omega c by pi, that is f1 is greater than 2 omega c dash. So 2 times the maximum frequency, this is the cutoff frequency, then it is 2 times in T1, then T in this direction, and it is also followed in the other way, that is 1 by T2 is greater than omega c double dash by pi, which is f2 greater than 2 omega c double dash. So here the Nyquist sampling theorem is it's greater than or equal to, then we can easily get the reconstructed signal back. So here it is followed, if we use this greater than, at least greater than or equal to, is also would result in this. For this spectrum, if we use greater than 1 by T1 is greater than, or this frequency, sampling frequency for in the FS1 is greater than 2 times the omega c dash, and similarly f2 is greater than omega c dash. You can see the pattern repeating in this direction as well as this direction, and when 1 1, so the same pattern is getting repeated. This is the similar to the case of 1D sample. So where omega c1, this is omega c T1 and omega c double dash T2, the omega c dash and double dash are used to differentiate this omega 1 direction and omega 2 direction, and this is 2 pi, and it's centered would be at up to 2 pi to minus 2 pi here. Okay, so similar fashion. This is the one without any aliasing. You can see this can be easily recovered using a low pass filter, a 2D low pass filter. With this portion of the figure can be recovered by eliminating or the filtering out the remaining pattern of the basebands, or the repeated one which is due to the sampling operation. And here this is followed, I mean the sampling frequency is greater than 2 times the maximum frequency. It is going to be greater than or equal to the as per this. So no aliasing in this case. But if x of the continuous time signal can be recovered from this samples x of n1 comma n2. So if we take the case where this is less than omega c dash by pi, that is under sampling, we did not follow the omega c dash is the maximum one, that is 2 times that should be sampling frequency, but this sampling frequency is less than that in both the cases. Then what happens, you can visualize here, this is the baseband, and the aliased components are overlapping, can be observed in this here also, here especially in this colored ones. You can see those are the aliased portions, so which were separated in the previous figure. Now there is a overlap between these patterns. Okay, so there is a overlap here as well. You can see the overlap which is marked here, that is nothing but aliasing. Aliasing in the case because it is the sampling is condition is not satisfied. So this 2D sampling, the concepts which we had discussed for the 1D sampling very well extended to 2D, and we can visualize it in omega 1 and omega 2. We will also use this, test it in the images for the signals, and how the sample the sequence will result in the aliasing portion. How does it look like in the images? Though we are using the digital images, continuous one, and then discretize it, or the sample it, and then the sampling if we follow, obviously this overlapping causes the distortion in the image. So how this distortion would be, how to remove these distortions if the sampling, if there are overlapping or distortions, it would appear as noise or at different frequencies. The high frequencies would be appear as in low frequency and so on, so due to aliasing. So that should be dealt. It is difficult to recover this, we cannot recover this from the xc of t1 d1 cannot be recovered from the samples x of n1 comma n2 here. So now with that background of sampling, you can get into the Fourier analysis. So this is known already, that is the Fourier time domain and frequency domain mapping. The continuous time signal is in the frequency domain. If you analyze it with the Fourier one, then it would give aperiodicity, and discrete signal would result in periodicity. Periodic one will result in discrete, and aperiodic would result in continuous. It's just a mapping from time to frequency domain. So this would result, what are the type of signal you have, and what is the Fourier analysis we have to choose to get into the frequency domain here. So if the signal is continuous and periodic, because of continuous in nature, this is CT, continuous time, a continuous time Fourier analysis. That is, if it is periodic, you get into the Fourier series. If it's aperiodic, then it's a Fourier transform. So similarly, for discrete times, Fourier series and Fourier transform, if this, because based on the signal nature of the signal, it is periodic, then it could be represented with this Fourier series, and then, or the aperiodic, it can, Fourier time transform would help us to analyze this particular signals. So our focus would be this discrete, periodic and aperiodic sequences, that too in 2D. So to know the background of this in the 1D, and then we'll do few of the examples, and then we look into these transforms in 2D. So the spectrum, when we apply this continuous periodic, the continuous nature is mapped into aperiodic in the frequency domain, and periodicity introduces discrete. So the spectrum would be discrete and aperiodic in this case. So similarly here, this is aperiodic and continuous, the spectrum. If we take the discrete periodic sequence, the spectrum is also discrete and periodic. Discrete and aperiodic sequence, then that would be periodic and continuous spectrum, so DTFT. So this would be very much useful, and in the 2D also, it is called the DSFT, discrete space Fourier transform, DTFT, and there is other transform which is DFT, discrete Fourier transform, that is going to be a sampled version of this DTFT, that we would see separately, DFT in 1D as well as 2D. So we are taking this, just giving the analysis and synthesis equation. Anyway, we are not going to deal with this CTFS and CTFT in this course. So this is an analysis equation where xt is a continuous time periodic one. So you get e power j 2 pi k omega naught. K is the values in which you get the frequency bends, and the synthesis one is this is for continuous periodic, and CTFS, it results in aperiodic and discrete spectrum in that. So aperiodic and discrete spectrum. So you have the discrete spectrum, that's the result of the coefficients. So these are the coefficients you get here in the frequency domain, and using those coefficients you can get back the sequence. This is an inverse transform. Okay. So then rest of this is a very elementary thing here. And CTFT, the continuous time Fourier transform, which is applicable to the continuous and aperiodic sequence, the spectrum would also be, when you say continuous, you need to integrate it with this is omega x of t e power minus j omega t to get the spectrum. If you know the spectrum, and you can get back this x of t through the synthesis equation, because both sides it is continuous, so the integration is applicable. Whereas in this case, discrete, it is discrete, result in discrete, so you have to sum it up, not the integration. So the case of DTFS, discrete time Fourier series, where a signal is discrete and periodic also, the pattern is repeating, and the spectrum would be in the same fashion, periodic and discrete, after applying this DTFS. What are the information it gives, and we would see that through the examples. So the coefficients x of k are ck, both the ways different notations can be used. So equal to 1 by n equal to 0 to n minus 1 x of n e power minus j 2 pi k n by n. So this factor is introduced in the DTFS. This factor can be here as well, so any one of this would be applicable, that's fine. So you can use it here, 1 by n x of n is varying from 0 to n minus 1, and to get back the sequence, so using this ck and sum it over, because it is discrete here, the discrete, and then get back the sequence, where omega is 2 pi by n, which is over here, 2 pi by n can be simplified as omega n. These were the periodic sequences. If the same discrete sequence which is aperiodic, then have the x of n, this is DTFT, x of n e power minus j omega n, where n is varying from minus infinity to plus infinity, get this x of e power j omega. It can be x of omega as well, the notation means the same in the DTFT. And the synthesis equation is this, it is 1 by 2 pi minus pi to plus pi x e power j omega, get this spectrum what we get here, and because it is continuous, The spectrum is continuous, we have to go for this integration to get back the x of n here. So we would see this few examples of the DTFS and DTFT. Suppose it is an infinite length sequence. For example, x of n is given. How do we find the coefficient of it? So it's a periodic sequence. Obviously, for DTFS, to obtain the a periodic sequence is given, obtain the coefficients of it. Then which one you would go for, whether it is periodic or not. You need to analyze it whether it is periodic if or not. If it is periodic, then go for the DTFS. Get the coefficients to analyze it. What are the frequency components in this sequence? So x of n is given, and whereas these amplitudes are mentioned over here, 1, minus 2, 2, and you can see the pattern repeating. This pattern is repeating over here. Suppose if you take it from here to here or to here to here, this pattern is repeating. Okay. It has 1, 2, 3, 4, 5 samples. So n is 5, or you can take the periodicity x of n equal to x of n plus n, where it is same. The periodicity property already in 1D we had discussed, and 2D as well, that is row wise periodic and column wise periodic. So this is periodic with capital the fundamental period equal to 5. So for that, to obtain the coefficients 1 by n, the equation which is the DTFS equation we use, and get the n varying from this. N is 5. So substituting over here, x and samples are known, and x of 0, expand this summation, x of 0 and here 0, and for different values of k, this is ck equation. So for we expand it, if this is the case with respect to k, the coefficients x of 0, x of 1, x of 2, x of 3, x of 4, there are 5 samples in that period, and what is the x of 0 value, can substitute it here. This is my 1 minus 1 by 2, 1, and this is 0, and here is 0, and this is 1 by 2. So if you get this equation, so this equation results in 1 by 5, 1 plus this k and k. So what is the ck? What are the coefficients exist in this? So if we put k equal to minus 1, this would yield a complex value which is given here. Also minus 2, so would give the value here. C of 0, k equal to 0, 1 by 5, because these things would become 0. So you get only this DC component. So k equal to 0 represents the DC component which is present in the signal, and k equal to 1, putting k equal to 1 in this sequence, get a value which is showing that there is a fundamental present in it, whose magnitude and phase are having these values. Magnitude and its phase is this. That phase is with respect to the cosine component samples of the sequence that we would see more or less in the DFT case. So now see, there is a fundamental component present in it. 2 also yielding a value, k equal to 2 is giving a value which is showing that there is a presence of second harmonic. These are in the negative k values. This is same as this. I mean, you can say the conjugate of it, or if you go from 0 to 4, 0, 1, 2, 3, 4, 5, up to that 0 to 4, n is equal to 5. In that case, we can see in the spectrum 0, 1, 2, 3, up this is for n number of samples in which k is varying from 0 to 4 here, and then 5 and so on. It would continue like this, and you can see the spectrum, phase spectrum also 0, 1, 2, 3 and then 4 here, and it would continue from here. This is repeating. So in DTFS, the spectrum is discrete and it is periodic as well. So this would be repeating after. Similarly here, this pattern comes over here. So you can see this pattern is getting repeated everywhere. This pattern is getting repeated. So this is also periodic and discrete, magnitude and phase spectrum, and moreover this is even symmetry and this is odd symmetry. So the symmetricity also could be observed from it. That's a property of this DTFS. We can get the information. This means k equal to 0. It is the presence of DC, presence of fundamental, second and third harmonic, and then fourth harmonic as well in this sequence. Okay, so but the phase shift is 0 for this DC, and here is there is a phase shift, and phase shift here is negative, and there is a phase shift. So this is for one period of the signal. N is equal to 5 get taken. So this is the interpretation of the Fourier analysis for one dimensional cases. This is also true in the case of 2D. So DTF, if it is a periodic sequence of discrete nature, so then we apply this DTFS, discrete time Fourier series, and then get these coefficients. If the coefficients are given, then you can get back the sequence as well. So from this coefficient you can get back this sequence. So one example for a finite length sequence in which x of n is 1 1 0 0. Take, if there is nothing mentioned, just take this point as n equal to 0. It's periodic with n equal to 4, that is 1 1 0 0 is getting repeated. That's why we go for this DTFS. This is a discrete sequence and it is going to be periodic. So for one period we compute this CK coefficient. So we know this 1 1 0, this is these two samples and other samples would be 0 for this. So 1 by 4, 0, n is varying from 0 to 3, and if we expand it, C0, this CK coefficient, in which this would result in 0 and giving the value of 1 by 2, and C1 results in a value of 1 minus j by 4, and C2 is 0 and C3 is 1 plus j4. So we can observe something here. See, it has a DC, okay, this sequence, and it has a fundamental as well. And you can see that is this is doesn't C2 is 0, it doesn't show anything, I mean it's absence of it, and 3 is having 1 plus j4. So you can observe the relation here, these two things. This is a complex conjugate, isn't it? So C1 and C3, both are the complex conjugate. C3 is a complex conjugate of C1. So it is sufficient to calculate up to n by 2 terms of K. Did not calculate here, n is 4. So it is sufficient to calculate K equal to 0 and K equal to 1. K equal to 0 to 1. 2 and 3 are 0 is DC and 1 is going to be the value of the whether the fundamental or not. 2 is the case where it is 0, it is not having, and these two, this is a complex conjugate. So it is enough to find out up to n by 2 independent components. You can get n by 2 independent components in the DTFS. This also will be true in the DTFT if we take it. So we'll also discuss that similar argument in DFT. So it is sufficient to calculate 0 1 2, and it need not calculate 3 because 3 is known, it's going to be a complex conjugate of this C1. Okay. So if it is n equal to 8, then calculate up to 0 1 2 3 4, and 5 6 7 would be 1 2 3 4 5 6 7 in this case. So you calculate up to 4, this would be a complex conjugate, and this is again a complex conjugate, and this would be a complex conjugate of it. So it's sufficient to calculate up to 4, and this need not be doing the computation for 5 6 7. And C4 is 1 by 2 here, so which is again repeating. You can see after n samples in frequency domain, so 1 by 2 is getting repeated here. That is C5 would again go up like that, C5 C6 C7 and so on. This would be a periodic, because it is periodic, this would also be periodic. Now the case of magnitude and phase spectrum. So whatever we got, this DC fundamental and second harmonic is absent, so it is 0. In the magnitude it is giving 0, and the phase is not known. So phase is not 0, phase is undefined here, C2. This is 0 and this is minus pi by 4. So you get the spectrum, magnitude and phase spectrum from this. So we can get the inverse DTFS for the case a sequence x of n. Get this x of n for a given coefficient. So suppose this is the inverse transform. So given the coefficients are all 1 by n. For it is minus 3 to plus 3. So taking it for a case of k equal to 0 to n minus 1, because this is also going to be periodic, take it for a period and use this coefficients and get back the sequence. So in this case, this is going to be k equal to 0 to n minus 1. So it is 1 for all these values. So 1 by n into n, that's going to be 1 for 0, x equal to n is 0, x of 0. If you compute it for 1, just changing this value to 1, this is an expression in which we can have it like this coefficient is 1 by n e power j 2 pi n. K is going to be the a of a to find the closed form solution. So that is going to be 1 by n into n 1 minus a power n, because this is this limit is up to n minus 1 only, n minus 1 plus 1. So this is going to be n, and 1 minus a, whatever this, if this is a, going to be 1 minus a power n minus 1 plus 1. So this is what, this is how you end up in this. This is going to give 0, because 1 minus 1, this is giving 0, x of 1 is 0. So similarly for n equal to 2 and other things, if you calculate it is 0. So it results in, at n equal to 0 there is a 1, and remaining are zeros, and after this again pops up at n equal to n, okay, 1. Again this is a repetition, again discrete. So what we try to say, this is an impulse sequence here, and in the frequency domain it has all frequencies. So that's what we can observe here. This is containing all the frequencies, and it's an impulse train in the case of x of n. Okay, so this is a Fourier transform pair. And coming to the DTFT, discrete time, but this sequence, if you see, it's aperiodic. So if you plot it, this n can take both the values, so 0 as well as positive and negative values. So positive and negative values, if you plot it, it would be like this x of n is here, and exponentially decaying sequence for different n values. This is n, and similarly it would also be 1, because it is a is less than 1, it would be a decaying sequence. So this would follow in n negative direction, and this is for positive, and n equal to 0, it's also valid. The sequence is two-sided sequence. So for minus n, this can be written like 1 by 4 n, this is the u of n, right sided, and 1 by 4 for minus n, for u of minus n, this one, except n equal to 0. At n equal to 0, this is simply an impulse. So minus del of n, because we have included the del of n in the right sided sequence 1 by 4 n u of n. So that should be subtracted to represent this sequence. Otherwise this would be again one more del of n if you put that del plus here. So this is sequence. Now finding the DTFT, n is very minus infinity to plus infinity, x of n e power minus j omega. So separately find for DTFT for all the three. That is, for this sequence, this is x of n, the first portion, and the second one similarly this, and this is for del of n, 3. So this, the closed form solutions we can obtain 1 by 1 minus a for this. This is also similarly we inverse the n, that is minus n equal to minus n here, that m equal to minus n, you replace this with the variable and get the summation. 1 by 1 minus, as you can see the sign change over here, that's a small change, and del of n obviously it exists at least 1 at n equal to 0 only, so it is going to be 1. So this is the spectrum. You can see the continuous nature of it, and the continuous, though the discrete sequence results in a continuous omega. So the spectrum further simplification results in a computed like e power j omega is cos omega plus j sin omega, and then separate it, and then you get the simplification results in this function. So if you plot this with respect to omega and x of e power j omega, so it's a continuous function which is repeating. Discrete nature of this sequence results in periodicity, and this is aperiodic also here, that would make the spectrum continuous. So you can see the continuous spectrum. So this is the spectrum which we can vary the omega and plot these values, so you can get this spectrum here. So we can get this inverse as well. So the inverse one, using the property L of n minus n naught, the impulse is shifted. That means it is simply the multiplication in the e power frequency domain, e power minus j omega n naught. It's a Fourier transform of this. Then cos square omega, the sequence to get the spectrum is cos square omega. From that we get x of n in this. Cos square omega can be written as sum of these two impulses and square it, because it's a cos square omega. You simplify it, we will get the 3 terms over here, and apply the inverse using the inverse DTFT using the property 1 by 4 del n plus 2, and this is 1 by 4 n minus 2 here, and then you have del of n. This is del of n. So x of n is the sequence which is having the impulses shifted and has some magnitude for it. So though the spectrum is cos square omega, this is a discrete one and aperiodic sequence you would get through the DTFT. This is one example. So obtained x of n is plotted over here. 1 by 2 and shifted impulse, and this is another shifted impulse. So cos omega have the two impulses at that frequency that in the Fourier domain. So this is in the inverse case. So this sequence results in cos square omega in the if you take from x of n to x of e power j omega. So with that we have seen the Fourier analysis for the one-dimensional cases like the continuous time, both the cases, the periodic and aperiodic one. Though we will not be dealing with that, just represented this equation to know the spectrum, how the spectrum would be. The discrete sequences, whether it's periodic or aperiodic, similarly Fourier series and Fourier transform could be applied, and the spectrum nature of the spectrum should be known, so that you interpret the spectrum, how to interpret the spectrum, what we get, magnitude and phase spectrum, what is the meaning of that with the original signal, what you have analyzed is known from these examples. We have also done the continuous waves, that is sinusoids, and its aliasing part, and what is the apparent frequency, how to compute the apparent frequency can be understood from the examples we dealt with. We will continue the Fourier analysis in two-dimensional in the next lecture. Thank you.